so we will start talking about in the previous few modules. I have talked about the solution of Schrodinger wave equation for different model system, and we talked about in that series of the systems. We talked about simple harmonic oscillator and rigid rotors. Now I am going to talk about a real system, that is a hydrogen atom. In hydrogen atom, you have a nucleus which has one proton, and you have an electron which is orbiting around the nucleus. Whatever the picture of hydrogen atom you have been told till now is that there is a nucleus at the center, and around the nucleus there is an electron which is rotating. Uh, eh, Both in case of Rutherford model, in case of Bohr's model, the picture remains same, and even in the Bohr-Sommerfeld theory also the picture remains same. But we will try to find out that how the quantum mechanical treatment of hydrogen atom differs from these classical pictures. In case of Bohr's model, quantization concept is used, but a pure quantum mechanical treatment or applying Schrodinger wave equation to hydrogen atom changes the picture of Bohr's model also. And what does it changes? We will see. Okay, because the basic principle of quantum mechanics is that you cannot talk about the trajectory, and because trajectory specifies the position and the velocity, and uncertainty principle tells you that you cannot talk about the trajectory. So the concept of Bohr's model that electron is rotating around the nucleus does not hold good in quantum mechanics. We will see, if we apply Schrodinger wave equation to hydrogen atoms, how what kind of picture emerges for hydrogen atom. And the Schrodinger wave equation is what? It's what kind of Schrodinger wave equation we can use, because we consider this to be a spherical molecule. So again, the Schrodinger wave equation in Cartesian coordinate we cannot use. What we will use is the spherical polar coordinates, and which we have already I already introduced you in rigid rotor problem. So the difference between the other system and this hydrogen atom is that there is a potential energy because of the electrostatic interaction between the electron and the nucleus. You have one electron, you have one nucleus and one electron. So we have a nucleus at the center, and you have an electron like this one. So we say the force acting between the two, because the charges are same, so the force is E square by R square, and if you calculate the potential energy, it is minus E square by R. So this potential energy will be part of the Hamiltonian for hydrogen atom. Okay, so we can write the Schrodinger wave equation in Cartesian in polar coordinates as 1 by R square del by del R square del psi by del R. So this is your having only one variable R. Then the second term is 1 by R square sin theta del by del theta sin theta del psi by del theta. This has two variables, R and theta, and then you have 1 by R square sin square theta del square psi by del phi square. This has three variables, R, theta and phi. I talked about this in the rigid rotor also. Okay, and this whole is nothing but a converting del square psi Laplacian operator into spherical polar coordinates. So this is del square psi, and beyond that, what you have, plus 8 pi square m by h square E minus V psi is the Schrodinger wave equation. And if you replace this V by this potential energy, then you get the Schrodinger wave equation for hydrogen atom. So we have replaced here V by minus E square by R, and then you have the Schrodinger wave equation for hydrogen atom. See, the situation becomes a little more complex than rigid rotor, because in rigid rotor we supposed R to be equal to 1. And if you consider that, then this whole first part, radial part, this first part goes away, and you have this equation where you have only two variables, theta and phi. This R also goes, because R is equal to 1, this R also goes, so you have only two variables, theta and phi. But in case of hydrogen atom, you cannot take R is equal to 1. So R will remain there, and if we have three different variables, R, theta and phi. And as previously, the first thing which we will be doing is the separation of variables. So we have three different variables, r, theta and phi. So what we are going to do, you are going to split that wave functions of the wave function, this wave function psi, into three components, each depending on only one variable, and the total function will be a product of these three different functions. Okay. So what we do, we write psi, which is a function of r, theta and phi, psi, which is a function of r, theta and phi. We split this function into three components, capital R depending on r only, capital theta depending on theta only, and capital phi depending on phi only. This is the normal method. I said you time and again that whenever you have a wave function which has more than one variable, then you can split that wave function into component wave functions, each depending on only one variable, and the total wave function will be the product of component wave functions. And if you have a system like this and the energy is dependent on more than one variable, then you can break this energy into component energy, each depending on only one variable, but the total energy will be sum of the component energy. You remember this? We used psi x, y and z into x depending on x only, y depending on y only, z depending on z only, and energy E, x, y and z, and each of these energy Ex plus Ey plus Ez. So this I am saying time and again because these are something which you should never forget in quantum mechanics. Okay. So if you put this value, instead of psi we write r, theta, theta and phi, phi, then you see the previous equation, del divided by del r into psi, it was there. So we have placed this value here, we have placed this value here, and we have placed this value here, and we have placed this value at four different places, 1, 2, 3, and then you have psi here also. Okay. So now what we do, we are differentiating here in the first equation, we are differentiating with respect to r. So what does it mean? Theta, theta and phi, phi will remain constant. So you bring theta, theta and phi, phi here, it is a constant. Here you are differentiating with respect to theta, so r and phi will be constant, and r and phi you can write here. Here you are differentiating with respect to phi, so here r and phi will be constant, r and theta will be constant, so r and theta is a constant. So these are the constants. Now what you want? You want to get rid of these constants, so divide the whole equation by r, theta, theta and phi, phi. And by dividing this r, theta, theta, phi, phi will also go. Okay. So look at this one. If you divide by r, theta, theta and phi, phi, then you have 1 by r only. Here if you divide this by r, theta, theta, phi, phi, then you will have only 1 by theta. If you divide this by r, theta, theta, phi, phi, then you have only phi. And if you divide this by this one, you get nothing, it's 1. Okay. So the equation becomes a little simpler, and now you have this part where you have one r. R means function, capital R is a function, a small r is the variable. So function r, then variable r, then variable r, then variable r, then again function r, then again. You see in this part you do not have any r, any theta and phi. Let's see what else we can do. Then you multiply this equation by r square sin square theta. You see, if you multiply by r square sin square theta, r square sin square theta, if you multiply by r square sin square theta, what do you get? R square sin square theta, then this r square and r square will go, you will have sin square theta divided by rr. Just to tell you one thing, sin square theta divided by rr. Okay, here you will get sin theta divided by theta theta. Here if you r square sin square theta, so r square will go, and if you have this r square sin square theta, then this r square and this r square will go, and you will have sin theta only, sin theta divided by theta theta. So you have sin theta divided by theta theta, sin theta divided by theta theta. Okay. Similarly, if you do it here, r square sin square theta was in the denominator, so it will whole go, and you will get this one, and then multiplication of this last term is r square sin square theta. Okay. So then sin square theta divided by r, del by del r square, del r by del r, sin theta by theta theta, del theta, no change. Now I have brought this here. Here you see, in this part you have r square sin square theta. So but in this part you do not have any other variable, so I have brought this on right hand side, 1 by phi phi del square phi phi by del phi square. It's very similar to what we did in the rigid rotor. Okay, in rigid rotor also we did the separation. Okay, now what we can write? We can write this whole equal to m square, and thus this part, this and this together will make an equation which will be phi dependent only. Okay, but naturally if this is equal to m square, so this left hand side is also equal to m square. So we will start, we have separated one of the function, then we are going to separate the next two r and theta equations. Okay, for that what you do, you divide by sin square theta. So if you divide by sin square theta, this will go, and this will be 1 by sin theta, this will be 1 by sin theta, and sin square theta, so this will also go. So if you divide here by sin square theta, this will go. If you divide here by sin square theta, this will go, and if you divide it by sin square theta, this will go. Okay, and you will get an equation 1 by r del by del r square del r by del r plus 1 by sin theta theta theta. This theta theta will remain, theta theta del theta sin theta del theta theta by del theta plus 8 pi square mu by h square e plus e square by r. Again you see what we are using is mu. What we are using is mu. It is the reduced mass. I said you, we have two particles, one electron and one nucleus. In case of rigid rotor, we were having two atoms rotating in a diatomic molecule rotating in a plane. So whenever you have two particles, then you can use, instead of mass, reduced mass, and then the problem becomes one body problem. Okay, so this electron and proton business is now not there. It's the reduced mass which you are used, 8 pi square mu by h square. Okay, so this equation you get, and since you are divided by sin square theta, so this will also be divided by sin square theta, and you get this one. Okay, now we are very close to solving this equation. Now just rearrange this one, and you see here you have only r part, and here you have, this is also r part, and but this part has sin square, this equation, and this equation has theta part, m square sin square theta minus 1 by theta theta sin theta del by del theta sin theta del theta theta. So this is theta dependent, and this is r dependent. Okay, now two sides each having only one variable and must therefore be equal to the same constant which is supposed to be alpha. So now we equate these two sides equal to alpha, and then we can write theta part m square sin square theta minus 1 by theta theta sin theta del by del theta sin theta del theta theta by del theta is equal to alpha. Okay, now simplify this equation, and if you multiply by theta theta, what do you get? You get theta theta m square sin square theta, then theta theta will go, you will have 1 by sin theta del by del theta sin theta del theta theta by del theta into alpha into theta theta. Okay, and again you rearrange, what you get here is this one, this equation, 1 by sin theta del by del theta sin theta del theta theta by del theta plus alpha minus m square sin square theta 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 is equal to 0. Okay, what is alpha? What is m? Of course you know, because we did it in rigid rotor, but what is alpha? We will find out later on. But this equation is again separated, and now we have a theta dependent equation. Theta dependent equation. Same way, this part also will be equal to alpha. R part, LHS part will also be equal to alpha, and if you take that LHS is equal to alpha, then what you can write is this RR I have brought here, so it will be del by del R square del R by del R 8 pi square mu by h square e plus e square by R square RR. Okay, so if you multiply this equation by multiply by RR. So this will go, and here you in this in the second term you will have RR, and in the alpha part also you will have RR. Okay. So what the equation which you get is 1 by R square del square del by del R square del RR by del R. Wait. So where is 1 by R square? Where it is gone? 1 by R square. Then I have missed this 1 by R square, so you should write 1 by R square. Okay. Here also 1 by R square. Okay. Here also 1 by R square. This will be there. 1 by R square. 1 by R square. Okay. And then you have 1 by R square. Okay. So these are the equations which you obtained. A phi equation, del square phi phi by del phi square plus m square phi, and theta equation is 1 by sin theta d by d theta sin theta d theta theta by d theta plus alpha minus m square sin square theta 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 is equal to 0. If you go back to your slides of your previous modules, our previous modules, and you see the rigid rotor solution, then you will find that these two equations are exactly same as we found in rigid rotor. There is no change except this alpha was beta there. That's all. Okay. The only change is that this alpha I have written as beta in case of rigid rotor. Nothing except this, there is no change. The R equation is a different equation which we did not get in rigid rotor. We did not get because R was constant there and R was unity there equal to 1. Okay. So the R part we omitted, and we suppose that the rotation between the bond between the two atoms is constant and it doesn't changes and it has a unit value. So in case of rigid rotor we did not get the R equation, but theta and phi equations remain same. So the solution also this we have done. This solution is very easy because it resembles the particle in a one-dimensional box, and all the boundary condition for this phi equations and theta equations remain same, because the phi varies from 0 to 2 pi, that you know. The phi angle varies from 0 to 2 pi, theta angle varies from 0 to pi. Okay, so the boundary condition also remains same in the two equations, and the solution will also be same. And if you use the same solution with this, we have this table was there also, phi and equation and theta equation. So for m is equal to 0, and when we solve the phi equation, we got m value, that is magnetic quantum number value, and when we solve the theta equation, we got L value, that is azimuthal quantum number, and the significance of these magnetic quantum number and azimuthal quantum number we talked about in the previous module when we talked about rigid rotor. Okay, so this phi naught is equal to this one, it's the same thing. Then with plus 1 you have exponential plus minus I phi, with plus minus 2 you have exponential plus minus 2 I phi, and again with plus I you have this one. Okay, the theta equation is cos theta sin theta 3 cos square theta minus 1. All this equation we talked about, it's the same equation which we talked about in the rigid rotor. Because the equation is same, the solution is also same. Okay, and then if you combine these two part, phi part and theta part, then this together is shown as YLM, and this is called spherical harmonics. This tells you the angular dependence. Angular part of wave function of hydrogen atom. Yeah. Now you see the wave function for hydrogen atom will have two different parts. One is R dependent, another is theta phi dependent. So theta phi dependent part which is together called as spherical harmonics, will determine the change in the function in with respect to theta and phi. That's so we say that this tells you the angular dependence. But the tragedy is that in all these equations you find this imaginary value I here also, I here also, here also, I here also, I. Okay. And if you want to physically interpret, you cannot interpret it because physical interpretation is possible for real functions, not imaginary functions. Okay. So we can convert this spherical harmonics YLM in real forms, and for that the fundamental relationships which you have to use is exponential I phi plus exponential minus I phi is equal to 2 cos phi, and exponential I phi minus exponential E minus I phi is equal to 2 I sin phi. Again, you remember the product also has this value. Okay. Now if you want to do this, then the degenerate functions. Now what happens that if you look at the previous functions, 1 plus 1 and 1 minus 1, these two functions, y0 plus 1 and y0 minus 1. Okay. What does it indicates? It indicates your L is equal to 1, M is equal to 0, and then again, so M will have 0 and M will have plus minus 1. Okay. So here you have L is equal to 1, so this should be 1, this also should be 1. Okay. M value will be 0, L value is 1, LM value. So L is 1, L is 1, L is 1, M is 0, plus 1 and minus 1. Okay. So these are the corrections which you will have to make. So I'm doing it simultaneously. Okay. So we have these two functions, y plus 1 is exponential I phi and y minus 1 is exponential minus I phi. What we do is that for finding out the real functions, we take a linear combination of these two functions. We linearly combine them, a linear combination. And what does it take? You see, when you take the linear combination, means you take 1 plus 1 and 1 minus 1. You see the corrections I did. 1 plus 1 and 1 minus 1. Then this we show as it's a positive combination, so psi 1 plus. This is different. This is not your quantum number. This just tells you that we have linearly combined two functions, psi 1 plus 1, where this first one is your L and second plus 1 is your M. Here also the first one is your L, second is minus M. Okay. When you combine these two together, you should get this value. But if you combine these two together, 1 plus 1 and 1 minus 1, then this we show as representing this combination, a negative combination, by 1 minus. Then here you also get an I value. So what we do, we multiply it by a coefficients 1 by root 2 here and minus I by root 2 here. Why do we multiply this? And from where it comes? It comes from exactly arbitrary functions, but when we multiply this with this function, the function which you get is easy to interpret and it becomes real function. So we multiply this one because this will keep the function normalized also and real also. Okay. And from where it comes, is there any derivation? People have done it and found it to be the right kind of coefficients, so we are using it. Okay. We are not the first one to do it. So, so the reason for multiplying by 1 by root 2 and 1 by minus I by root 2 is necessary to keep the function normalized and real. Okay. So try to find out this linear combination, what kind of linear combination you get. You see, if you take a positive combination psi 1 plus, then it's 1 by root 2 root under this factor we have added, and the function was 3 divided by 8 pi sin theta e to the power I phi. and then root under 3 divided by 8 pi sin theta e to the power minus I phi. Just confirm this one, that whether this is the function. See, 3 divided by 8 pi sin theta e to the power I phi and root under 3 divided by 8 pi sin theta e to the power minus I phi. Same function we are using, and a positive combination. Okay. So if you positively combine this, what do you get? You can bring this 3 divided by root under 3 divided by 8 pi sin theta outside, and then you have this function. Okay. Now from de Moivre's theorem, e to the power I phi you can write as cos phi minus plus I sin phi, and this you can write as cos phi minus I sin phi. So this equation if you use, then what do you get? You get 2 cos phi. Okay, this and this will go, and 2 cos phi, and a combination of this, a direct relation also I have written, that e to the power I phi and e to the power minus I phi is equal to 2 cos phi. Okay, so this you could have written there with one more step as cos phi plus I sin phi plus cos phi minus I sin phi. So these two will go, and you will have 2 cos phi. Okay, and since it is 2 cos phi, 1 by root 2 is here. So you combine this 1 by root 2, it comes out to be psi 1 plus comes out to be root under 3 divided by 4 pi sin theta cos phi, and now you have a real function whose normalization constant is to the real function, and normalization constant is root under 3 divided by 4 pi. Okay, so this we can write very easily. Okay, once you have this function, similarly you can have a negative combination also, and if you negatively combine a negative combination psi 1 minus, then you have a minus sign here. Rest of the function remains same. This is the same, this is the same. Okay, but a negative combination is there. And what does this negative combination means? You have e to the power I phi minus e to the power minus I phi, and if it is so, then you have cos phi plus I sin phi minus cos phi plus I sin phi. Okay, because it will be a negative combination, so this will be, now these two will remain and this will go. So you will have 2I sin phi, 2I sin phi. This I has to go. Okay, so this is minus I, and now this, if you multiply with this one, this will go, because it's minus I, it's I, so this will go. It will be I square. I square will be minus 1, minus will be plus 1, so it will go, and rest of the thing will remain same. 2 is there, root under 3 divided by 8 pi is there, so this is the combination sin theta sin phi. Okay, so this is again a real form for psi 1 minus, and now it is physically possible to interpret, because now we have the real form of the equations. So whenever you have a spherical harmonics which contains imaginary number, then you can convert these spherical harmonics into real forms in order to interpret it physically. Okay, and this interpretation is important. Orthogonality we will not do. Okay, so this interpretation of is important because this will give you the angular dependence of the wave function. Okay, the second, this was the angular part, phi equation and theta. We did not do the solution. The solution was already there because we did it in the rigid rotor problem. Okay, so now the third equation which we get is R equation, and R equation is again will be solved in details, because the R equation tells you that how does the function depends on R variable. Okay, and this is again a power series method which we have used in simple harmonic oscillator, which we have used in theta equation of rigid rotor. In case of simple harmonic oscillator, Hermite polynomial and Hermite equation came into picture. In case of rigid rotor, theta equation, Legendre equation and Legendre polynomial, associated Legendre polynomial came into picture. When we will solve the R equation, we will see that here you have another polynomial called Laguerre polynomial, and associated Laguerre functions will come into picture. This we will do in the next module. Okay, thank you.